Hi everybody, this is SAAD for the SAAD Truth. Apparently I can't stay away from you guys for too long. I seem to be cramming as many SAAD Truth clips as I can prior to my much needed break. In any case, today I thought that I would discuss with you three problems that I first encountered as an undergraduate student in math and computer science. These were incredible problems to work on. And so they've always stayed in my mind. But I also used some of those problems when I subsequently became a professor and I taught psychology of decision making. I used those problems to highlight the types of cognitive doggedness that people sometimes succumb to when they're trying to solve a problem and they can't extricate themselves from what looks like a wrong approach. But in any case, I thought that I would state each of the three problems and see if someone can solve one, two, or maybe three of them. So let's see if you're up to the challenge. So problem one, this comes from a course that I had taken with Professor Monty Newborn at McGill University. He was actually somebody who was involved with the Deep Blue project. This is the computer algorithm that was used to play against grandmasters of chess. It was just an amazing course that we had taken. I just loved it so much. And so this first problem comes from his course. If Professor Newborn somehow watches this clip, maybe I'll send it to him. I hope that he'll be pleased that 30 years later, I still remember the wonderful and challenging assignments that he gave us as his students. So here we go. So the first problem goes as follows. Suppose you've got 12 coins, 11 of which are of equal weight, and one is a counterfeit coin. Now, what is the minimal number of weighings? So if you had a balance, how would you take these 12 coins, and what would be the sequence of weighings, and what is the minimal number of weighings that you would need so that you're able to not only identify which of the 12 coins is the counterfeit one, but also whether it is lighter or heavier than the other 11 coins. So that's known as the counterfeit coin problem. Don't cheat and Google, see if you could solve it yourself. And again, the question is not whether you could find a way to, find which is the right coin and whether it's heavier or lighter, but it's to do so in the minimal number of steps. So what is that minimal number? Is it 5 weighings? Is it 6? Is it 3? How many is it? What is the minimal number that you could get to the solution? So that's the first problem. The second problem, also from Professor Newborn's course, he's really going to be pleased here with me in that I remember these two assignments from 30 years ago, 30 plus years. I think it was in 1985, 86 that I took his course. So let's suppose you've got a string, a binary string made up of zeros and ones, right? So, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1. Okay, that's a string. Now, it's a two-person game. Player A starts, and he or she can remove one of the two digits at the ends of the string, right? So, for example, I could look at the string and remove the leftmost digit. Then when the next player's turn comes up, he or she can remove a digit from either end of the string. Again, you could only, when it's your turn, you could only remove the leftmost digit or the rightmost digit. So here's the question now. This is an incredible problem. Is there a way to look at the string prior to the start of the game and to offer the set of criteria that in looking at the string, you would know who's going to win the game? Player A or player B. Do you follow what I'm asking? So this is a deterministic game. In other words, there is a set of specific markers or criteria or characteristics of any string that I could look at and say, oh, based on this reality, player A will win, or based on this reality, player B will win. So let's see if you could find it. So tell us, what are those criteria that would allow us to know ahead of time, a priori, who would win the game? Third problem, This comes from a discrete mathematics course that I took with Professor Rattray. Again, I hope that these professors, I will try to send them my link, but I think that, regrettably, I think that Professor Rattray has passed away. I did a quick Google search and I didn't check very carefully, but I think he might have passed away. This is yet to be confirmed. But in any case, in his course in discrete mathematics, we looked at all sorts of really interesting problems in graph theory, something known as the pigeonhole principle. There are all sorts of really, really cool permutations. I'm trying to remember all the stuff in discrete mathematics. But anyways, one problem that we looked at is the following. So let's see if you could solve this one. Suppose you have n people at a party, okay, whatever n is. Could it be that each person at the party knows a different number of people at the party? And here, when we say know, it's reciprocal knowing. So if person A knows person B, this means that person B knows person A. So it's not one directional knowing. Okay. So in other words, the question is, for example, one person knows 7 people at the party, another person knows 10 people, another person knows 3 people. Could it be that every single person at the party knows a different number of people at that party? In other words, if, for example, person A knows 3 people and person B knows also 3 people, that means that 2 people both know 3 people, and then that would violate what I'm asking. Okay, so let me ask it again. There are n people at a party. Could every single person at that party know a different number of people at that party? So there you have it, 3 problems. The counterfeit coin problem, the, let's call it the binary string problem, and the, let's call it n party or n knowing at the party problem. So no cheating. Let's see if anybody could solve any of them. I'm very curious to know if people do solve it or not. Now again, forgive me if I don't sit and read all of your comments. I'll try to periodically in the next 24 hours or so look to see if anybody's gotten it. Best of luck. No cheating. Go ahead and solve those problems. Cheers.